This laboratory session, laboratory number 3, is based on a final exam problem I once gave. It's a plate that rests upon a support at midspan, and the idea was to see how much of an end twisting load on this cantilevered plate is reacted by the support and how much is transmitted to the wall. The ultimate goal will be to find the deflection at the cantilevered tips of the plate. We'll state the problem and then show physical modeling and then finite element modeling. I'll continue with the data sets for the 3 different commercial codes that we'll use, and then we'll discuss the results with emphasis on the displacements this time. We'll start with our discussion of the problem statement. Here we have a rigid wall with an elastic cantilevered plate projecting from it. But at the midspan in this side view is a support. The support is pinned to the bottom of the plate. The plate itself is not hinged. It's a continuous plate through here. And the support is of a type like a piano hinge with knuckles that prevent the plate from sliding along the length of the pin here. So the plate is captured, in fact, in 5 of the 6 degrees of freedom and only can rotate about that pin. The plate is made of aluminum and it's 10 millimeters thick. It is 1 meter in length and ½ a meter in width. The hinge support lies under the midspan shown here. And we'll pick a coordinate system at the lower left corner with X and Y lying in the plane of the plate and Z upward. Our goal is to find deflections under the load. With that problem statement, now we need to make some physical assumptions. The material is thin and flat. The 10 millimeter thickness is much less than the 500 millimeter width, so it's more than a 10-to-1 ratio. In fact, it's 50-to-1 in the most critical dimension and 100-to-1 in the other direction. So it's quite thin. And we can use the Kirchhoff-Love plate theory here. That will assume that plane sections remain plane and perpendicular to the neutral surface of the plate. The loading that was shown was a twisting pair of loads, and it's assumed to be normal to the plate neutral surface. We're going to assume small deflections and slopes. Now, this can be pushed a little bit in the case of the free end of a plate because although you may get to a plate thickness, you do not induce large membrane stresses by doing so. So as long as our deflections are on the order of the thickness of the plate or less out at the tip, we're probably okay. If they're on the order of half the thickness or so in the interior between the wall and the support, we're probably okay. We'll assume that the material remains linearly elastic. And since the loading was perpendicular to the middle surface and then the response is small, we're going to get what's called pure flexural response. There won't be a tensile membrane set of forces developed. The boundary conditions at the wall are assumed to constrain all the degrees of freedom because it's rigid. And as we've mentioned, the boundary conditions at that hinge support will constrain 5 of the 6 degrees of freedom but allow the rotation about the y-axis. There is a reflective plane, and we're not going to exploit it, but with those anti-symmetric loads, you could in principle model half the problem with anti-symmetric boundary conditions. Now that plane of symmetry runs longitudinally through the plate, normal to the wall. We now move to the finite element modeling. And we're going to use 6 4-noded elements in each of our solutions. These are called quad 4 elements in the NASTRAN series. We won't exploit the reflective plane. We could have indeed cut the body in half and study perhaps the near half using anti-symmetric conditions. And when you do your lab assignment, if you carry this project out at your local installation, you may want to try that just to test your wings. The degree of freedom 6, which is rotation about the z-axis, should be made 0 at every node because of the defect in the Kirchhoff-Love plate theory that says there's no stiffness in that direction. Now there are some elements being created that attempt to overcome that, and there is a family of plate elements in MSc NASTRAN that tries to eliminate that requirement for constraining that drilling degree of freedom. At the wall, then, we'll constrain degrees of freedom 1 through 6, and that's at these 3 nodes to the left as the plate's laid out. And at the hinge, we're going to constrain everything but degree of freedom 5. So you see we've taken out quite a few degrees of freedom. The degree of freedom 6 everywhere, and then these others. Let's pause for a second and talk about the degrees of freedom in such a problem. This drilling degree of freedom that is notorious in plate theory is one that's omitted in the standard Kirchhoff-Love theory when the stiffness matrix is developed. So there's no stiffness associated with that degree of freedom, and that would become singular then in a stiffness matrix if it were included. So it's better to use a constraint, either an explicit constraint in some list of constraints or under an automatic single point constraint like the auto SBC in the NASTRAN series. Now some codes don't require it, and there are some MARC elements where that's not a requirement, and so it could be that the different commercial codes are going to work with that drilling degree of freedom in different ways. On the other hand, beams contribute all 6 degrees of freedom when you include flexure about both planes, and then when you have stretching and torsion on top of that. Plane stress, however, would only have 2 degrees of freedom at a given node, namely the in-plane degrees of freedom. A truss, strictly speaking, only has the on-axis stiffness. And if it were a torsional member, it would only have torsional stiffness. Springs can be generated in many commercial codes freely, and they can have from 1 to 6 degrees of freedom. Solids normally have only 3 translational degrees of freedom. So this really depends on the problem and the element choice as to how many of these various degrees of freedom will be present and will be active. Let's start with our data for this problem by looking at the MSc NASTRAN program and set that data up. We're going to use 6 quad 4 elements, modeling the entire plate. We won't exploit the reflective plane. Our first task is to set up the graphical output file. That's done through output 2, and it's put in a file called lab3.f12. The executive control statements will have the 2 ID words here, 8 characters each, separated by a comma. We'll have a time in minutes, and we'll use the solver 101. Now the older version, and this would be true in some of the cosmic programs, was Sol 24. 101 is the modern MSc version. Next come the case control commands. Titling your output, asking only for the sorted data, not the sorted data as I often claim, although some people think that finite elements does have sorted data. We do have to ask for displacements, stresses, element forces, and SPC forces, all of which are important. Particularly as you get into the structural theories, you like these element forces because those are the resultant forces, the moments and the running stresses, the shear stress and tensile stress, and so on. We only have one subcase, and we name the load for that as load 67, giving it a title, twist forces. Okay, then our bulk data entries. I will ask for the output for this problem for Patran, in the form for Patran. We will ask for the auto SPC feature in case we forgot to constrain, let's say, the drilling degree of freedom, then it would automatically be constrained. But we'll also use a grid set card and put 6 there, and that's kind of like a double killing off of the unwanted singularity. Let's look at the grid point definitions and the connectivities of the elements. The first 3 grid points lie at the wall, and so they're constrained in all 6 degrees of freedom. The next 3 grid points lie on the hinge support, and so they have 5 constraints embedded here, with only the 5th degree of freedom left free, and that's rotation about the hinge. The remaining outboard grid points are not constrained except for the drilling degree of freedom, which is removed, and that's done by the grid set card, which applies by default. Now on the element connectivity, we have the first 4 elements listed here. They are numbered 1 to 4, and then they point toward a property card, which is a P-shell card, number 25. I've chosen to number these in a counterclockwise direction. You could do it in either direction. You could start with any of the nodes, but usually it's preferable to do this in a routine pattern. And the reason being then that when you interpret stresses later, the sigma x and sigma y's have the same orientation. So be careful before you get real bizarre in the way that you call out the connectivity on such plate elements. We'll finish our bulk data entries here with 2 more quad 4 cards, and they point to a property card, namely the P-shell card here, number 25. That one in turn points down to a material card, 17. So we get our conventional set of 3 cards defining elements, namely a connectivity, a property, and a material card. Now the shell element here, the P-shell card is interesting because first you get the membrane material properties, then the thickness of the element, and then the bending material properties. Quite often I've found that people leave this second one out in a problem and forget to ask for flexural stiffness, and as a result you'll get a membrane model. I've had people do this in term projects where they model I-beams, and they think that they're doing it with plate elements, but they're really doing it with membrane elements if they leave this 17 out. I think you can argue a little bit with the default chosen here that since the first one mentioned was a membrane behavior, it shows the emphasis of membrane behavior in this element. And that's an aerospace philosophy where a lot of wings and bodies are designed with membrane analysis ideas only, and the bending is neglected. But most technical fields nowadays want to include bending stiffness of any sheet metal structure. Our material is aluminum, shown with Young's modulus, Poisson's ratio. The forces that we have under our force case 67, mentioned up in the subcase definition, are applied to grid points 10 and 12. With the basic coordinate system, there's a scale factor of 1, and then x, y, and z components. So you have one of them upward and one of them downward. And of course, this is what forms the twisting nature of the load out at the free end. Well, let's plunge into the results. And one of the first things I often look at are the forces of constraint. And here we have the vertical component, and here we have some of the moments. This is a little hard to see here, and I'm going to plot this on a common plot for the 3 codes at a later time. Now let's look at the displacement results for our NASTRAN run. And the 2 points that you would expect to have the greatest displacement, in fact, work out that way at grid points 10 and 12. And the numbers that are obtained are 10.56 millimeters. So we're pushing the linear theory a little bit with displacements this large, but we do have relief of any in-plane forces out at those free tips. So cantilevered beams and plates sometimes are allowed to go through that large a deflection without violating the linear aspects of the theory. I'll show you some of the stresses from NASTRAN. I'll print out the sigma x and then the maximum principal stresses and then the von Mises stress. Now, this is a rather abridged set of stresses then, because you can get much more information. I am printing out both the stresses on the lower surface and the upper surface as given by these distances from the mid-surface of the plate. When you look at the principal stresses, which is often a key indicator of stress, then there's always a positive and a negative stress in this bending situation. But you correlate the maximum principal stress at the one surface, say the bottom surface, and the minimum principal stress on the other surface. And so they pair up in this way across the little diagonal line here. Conversely, when you want to look at the maximum stress on the top surface, you'll compare it with the minimum on the bottom surface here. Now those two numbers are not quite the same, and the reason is that this twist is causing a certain amount of shear. So the picture isn't as clear as you might normally see in a body. The stress in the outboard 2 elements measured at the centroids here, as you get in a quad 4, is a little greater than the other stresses, so I call that out in red. And again, you pair up those extreme values. Now I'll show you some contour plots of stresses, principal stresses, a little later, and they continue this pattern which isn't quite obvious. So I regard the stress state as actually a little bit peculiar in this twisted plate. Now let's look at the MARC data for this same problem. We'll have our tidal lines here. We're going to allow 400,000 words of main memory. We're going to use element number 75 and look at stresses through 3 sections of the element. Presentation of output is controlled by the post command, and here we're asking for the 6 conventional stresses, both cases. And now we need to input the loads and connectivities. Point loads shown here, we have 2 cases following. First case here gives the z-axis loads of minus 1,000 and 1,000 newtons, acting on grid points 10 and 12. Then we're going to give 2 fixed displacement sets of data, and these are the single point constraints. Here we're going to constrain all 6 degrees of freedom at the nodes 1, 2, and 3. Then we constrain just these 5 degrees of freedom at nodes 4, 5, and 6. Notice that we're using the rigid format here rather than a free field. Then connectivity, we're going to have 6 elements. The first one of element type 75, and we give this set of node points, again in counterclockwise order viewed from above as we're doing. The location of the nodes in the MARC data set is found under the heading Coordinates. And here we see that we call for 3 coordinates at each of 12 nodes. And then those are shown here in the fixed field format. The number shown here, though, seems to be somewhat ignored by the program, and often if you use a preprocessor such as Mentat, it will put 6 in there. So don't be discouraged by that number. It seems not to be important. We now enter the material properties and the thickness of the plate. It's an isotropic material. We'll give one such set of data. And the Young's modulus and Poisson's ratio are given that apply to elements 1 to 6. There's one geometry involved with a thickness of 10 millimeters. It applies to elements 1 to 6, and that's the end of our MARC data set. MARC repeats quite a bit of the parameter settings that you have implied in your data set, and many times that's helpful to remind you what's going on. Here's such a chart that appears that lists many of the parameters in your problem run, including this one on number of points in the shell section. Now the results from the MARC run include these displacements, and our maximum tip displacements are the 10.6 millimeters shown here and here, just slightly greater than the MSC NASTRAN Quad 4 numbers. Now let's look at the single point constraint forces or reaction forces. In MARC, these are listed for all the nodes and for all the degrees of freedom, and they are either a reaction force or they're the residual load correction. So that would be the error in force balance. Now we pick up sizable numbers here, for instance in the z direction on grid point 1, but here at a point where there should be no such reaction because of the anti-symmetric load, there is some small error, just a small amount, and still much, much smaller than the other size of the forces elsewhere, so it's pretty negligible. In any event, these also are difficult to visualize from tabular data, so I will plot these elsewhere when we compare our different codes. The MARC element number 75 provides stresses at the Gauss points. I'll list those here, and the coordinates for the Gauss points are given, so you can locate where these occur on the plate. The layer is given, and the stress is given, and then the location of the Gauss point. Now we're not so interested in stresses here, so I won't follow this in detail, and besides this is such a crude model for stress. Let's turn now to the ASTROS data set. We're going to use 6 of their quad 4 elements. We have this solution control information first, similar to the other runs that we've had with ASTROS. Titles, assigning of a database, labeling figures, and printing the output of displacements and some of our stresses and forces and SPC forces. Let's look at the ASTROS bulk data. The first card is a grid set card, and this is to remove the drilling degree of freedom. That enters in field number 8. Notice that I'm using a free format here. Again, we have the grid as a signal that it's a location of a grid point. We have the identification number of the grid. Here we're taking the default coordinate system, which is the underlying or the basic coordinate system, and that's a rectangular right-handed coordinate system. We give the coordinates, and then we have a chance at a second coordinate system to present our results in, but choose to take the default again. And then we have the permanent embedded single point constraints at the wall. We do that for all three of the grids that lie at the wall, whereas for the grids that lie at the hinge support for the plate, we constrain 5 of the 6 coordinates, leaving the degree of freedom number 5 free, and that's the rotation about the pin axis. Then the grid set card takes hold for the remaining degrees of freedom and does that same constraint on the drilling degree of freedom. The remaining bulk data entries are shown here. Here are the connectivities for the quad 4 elements, and these in turn point to P-shell card, which has 10 millimeters of thickness for the plate, and that's going to act both in stretching with material 17 and in flexure with material 17. That material is called out as aluminum with Young's modulus and Poisson's ratio. We don't put anything in for shear modulus since it's determined by the other two. Our force cards here show that our load set 67, called out in the above introductory cards, is to be applied at grid points 10 and 12, and with magnitudes minus 1,000 and plus 1,000 to give us the twisting nature, and we end up with N data. The displacement results from ASTROS show that it's just slightly more flexible than the other two elements in this twisting situation, and you get some 10.9 millimeters of deflection at the tips, both plus and minus. I'll make a table and show how that compares with the others as we finish. Let's look at the forces of constraint for the ASTROS run. They're listed here for the 6 degrees of freedom where constraints have been applied. And those larger numbers then are the true forces of constraint. Also, though, when you get the smaller numbers at the other components, those are the round-off error, so it gives you some impression of the leftover forces at a given degree of freedom. Stresses for the quad 4 in ASTROS are given at the centroid of the elements. Here we see these values. And if this was important to us, we could position that on a plan view of the plate and show you where those values apply. I think because we're looking at displacements in this problem, we won't worry about that too much. Now let's gather our fragmented results together and present them in sort of a unified form. We'll also add the commercial solution. Here I've used the MSc NASTRAN results with Patran post-processing to show the undeformed mesh. The coordinate triad here is drifted away from its true origin at the lower left. The deflections are summarized in the following figure and chart, and this is basically the dominant results of our whole laboratory. Here I show that the deflection W max occurs both at the right corner and at the left corner as well. That number is shown here in the table and remarkably similar for the 3 codes, considering that it's quite a coarse mesh. So they range from 10.56 to 10.98 millimeters, all about 1 plate thickness. Now, I had to do a solution of this same problem in regard to some training I'd done about 4 years ago, and I divided this plate into many small elements on the order of 200, and the answer that I got was 12.18 millimeters. So that has got to be within 1% or 2 of the exact value. That was done with MSc NASTRAN. And so you can see all of our solutions are some 10 or 15% low. So we would need quite a substantially finer mesh in order to get really good deflection values here. I've made a contour plot of the lateral deflection for our plate. I used Patran for this. I was a little bit puzzled by the lack of symmetry of this figure, and over the last couple of years a student has discovered that if you would orient the element numbering in a way that was also reflectively symmetric, then the figure becomes symmetric itself, or anti-symmetric. That is, if I number these elements counterclockwise on one half of the reflective plane, as sketched here, and then I numbered the others in the opposite, in other words, the mirror image way, then the errors that are brought into the plotting package work out to give an anti-symmetric deflection pattern. So that's kind of interesting. It's a sort of a round-off error thing, I believe. But nevertheless, I thought it was clever of the student to observe that the original pattern for doing the nodal connectivities introduced a break in the reflective symmetry of the problem. I'll present the forces of constraint in 2 figures, the first for forces and then the second for moments. So here are the live loads shown with the flag at the top, and then the reaction forces to the left. The reaction forces at the fixed points on the reflective plane of symmetry should be 0 in this case for the anti-symmetric load. Now these numbers are not so different between the 3 codes, so it looks as if with this fine a mesh we're starting to get a little better resolution. So it makes you feel that all 3 of them are in the same ballpark. The constraint moments tend to differ a little more than the forces did from code to code. Not so much for the larger values, which are within 10%, but as you get to the smaller moments, you see that there are substantial differences. Actually, all of these codes are self-consistent. If you add up the moments and see how they react, what was the live moment about this x-axis, you'll find that each of those situations is in equilibrium. Let me present some contour stress figures. The first one is on the direct stress sigma x on the bottom surface of the plate, and it's given in megapascals. These are certainly not very high stresses that are being shown, and our mesh is so coarse that we're really pushing the plotter to make do with very little information on which to base such plots. So it's no wonder that we don't have perfect anti-symmetric stress patterns. Finally, let's look at the maximum principal stresses on the upper surface of the plate, and then we get this plot. I've pointed out one point from the MARC solution shown at its Gauss point, and it fits right in with the MSc NASTRAN solution.